Hello, this is Hamza Derek from Group 31, doing the Explainable AI for real-time micro-expression emotion detection. And we are going to, this is my presentation on the matter. These are going to be the contents of my presentation. It's going to have the introduction, literature review, problem statement, research questions, objectives, contributions, methodology, data set description, and preliminary results. Then we shall conclude with the future works and the anticipations for a future plan with the references. Um, First of all, to introduce this whole topic, microexpressions are brief reactions of the face that happen within a fraction of a second. To be exact, is about a 1 over 25 over a second. There are these tiny facial expressions that show a human being's true emotions that are very involuntary and they cannot be hidden. And that can be used, harnessed to see what a person really feels. And then in the papers that we read, emotion detection is a process of identifying the human emotion based on their facial expressions, which now leads back to the micro expressions. Then there's the explainable AI bit, which is a set of techniques intended to assist users in comprehending and reasoning behind the choices that machine learning models make. Uh, let's say there's the whole aspect of the black box and the white box, which we shall talk about later on in this presentation. And then what we're going to be using in our research is going to be LIME, basically, which is a local interpretable model agonistic explanations that we're going to use to be able to classify and get the different emotions that one is feeling. And then our models that we are training and that we have proposed on explainable, and they should be explainable and they should be real time. And then here are some of the literature reviews that we went through. This is basically an excerpt from all the different papers that we reviewed in order to come up with our proposal. And we basically considered these different categories because they're the ones that applied more onto our side, which was the ability for microexpression detection, the data diversity, the explainability, and the real-time processing ability. Then obviously there's going to be a bit of the transfer learning that we wanted to find out about, then the ethical considerations, then the deep learning extraction methods, coupled with the pre-training. Um, uh, Majority of the papers that we did review had the whole bit of the micro expression detection catered for and it was covered. Then the data diversity, which was a bit 50-50. Some models or some papers that we reviewed were using data sets that were not really diverse in nature. And then the explainability, which whereby majority of them did not have that bit of explainability. And then the real-time processing ability, still majority lacked that ability. Then a few had a bit of transfer learning covered, as we can see from here on these cited papers. And then the ethical considerations, majority of them were not clear or were unknown, but a few of them did give something in regards to ethical considerations. And then the deep learning extraction methods, then coupled with that pre-training. And the problem statement, accurately detecting and interpreting microexpressions is crucial for various applications, include lie detection, emotion recognition. However, traditional computer vision algorithms struggle in identifying microexpressions effectively due to the subtle nature and complexities of the facial expressions, and this has led researchers to adopt to deep learning models, which have shown promising results in real-time microexpression detection. However, deep learning models also have some vulnerabilities because of their black box nature, which hinders the transparency and interpretability which human beings generally fear if they do not know what is happening or they cannot tell what is happening behind the scenes. That has led to it being unpopular, reduced its popularity. But explainable microexpression detection fosters trust among users by providing insights into the model's decision-making process, which empowers developers to refine the model's accuracy, reliability, and advancing the research effective computing by revealing the underlying mechanisms. And if we are to look at the research questions and objectives that we followed in this whole procedure, one of the main objectives was to create a real-time expression detection system that accurately identifies, classifies microexpressions, but with the whole goal in mind of adding the interpretability and explainability of the decision-making process. Then there were a few questions that we had in mind that we needed to answer, which were how the microexpressions are going to be detected accurately from facial images. And then the research objective was to develop a deep learning model for real-time microexpression detection. And then there was a question of how can transparency and ethics be ensured within our model. Then it was to obviously to integrate the explainable AI, since people now can see into our model and know what it's basing on to make the decisions. And can the system be developed with minimized biases and improved fairness? And then to analyze the potential of biases, explaining microexpression detection was our objective. Then can the system be implemented and evaluated in a real-time setting? Then the whole objective of that would be to demonstrate the real-time applicability of explainable micro-expression detection in the system. And with all those in mind, we had to like now go into the whole process of finding out what this whole thing can do and what it cannot do. And with that, it led to these. We thought it would lead to these research contributions when we have studied the whole bit of real-time microexpression detection, and then to be developing a deep learning model for real-time microexpression detection, which was obvious. And then the other would be integration of explainable AI techniques within the deep learning model, then analysis of potential biases in the explainable microexpression detection system. Then there'll be demonstration of real-time applicability of the explainable microexpression detection system. Then this was the methodology that we had in mind and the whole process that we were using to come up with this whole explainable AI. The first bit would be to start with the data collection process, whereby we would get different images that we're going to use to train the model. Then there'll be the whole process of data pre-processing. Then there'll be a bit of explanatory analysis. Then from all that, then there'll be feature selection from like the data that we have collected. Then there'll be a bit of data splitting. Then from that, that's where the model will be trained from the data splitting. And the trained matrix will have like its evaluation matrix. But of course, with that trained model, there will be the problem, the black box. Then the whole point of the black box is whereby we cannot see what is happening or what the model is basing on to make its decisions. Now that's where we are trying to add the interpretability and the explainability within that AI, which will be coupled with like more training with a bit of transfer learning and all, so that we can be able to obtain a state of a white box, which is the most desired state. Then from there, we shall like get into the feedback loop and everything when the model has been implemented in its various applications. If we do move forward, we shall have the dataset description, whereby our dataset just consists of 41,000 carefully selected observations of facial expressions, and which was collected from reliable websites like Keigo. And then the dataset consists of 48 by 48 images of faces, and these will be including the angry, the contempt, the disgust, the fear, the neutral, the sad, the surprise, and the rest. And all these were collected over a period of about 30 days, if I'm not to be wrong. Then from there, if we can move forward to the whole results and then the whole outcome from this model, we have in the model evaluation. Proposed CNN model for facial expression recognition achieves an overall accuracy of 92%. The model struggles to predict contempt and disgust emotions with precision and recall scores of less than 80%. So below is the confusion matrix of how the model has been forming. And then from all this, we can see the different classes that were within the dataset. The one of surprised, then there was the one of sad, neutral, happy, fear, disgust, contempt, and angry. But from the confusion matrix, we can see that since majority of the images were happy, it can easily classify the happiness or the happy nature from someone's face. But then it was having a few problems with contempt and disgust and angry. The whole classification bit was a bit tricky for the model, and the predictions were a bit off, but we're planning to fine tune it in the nearby future. And then from that, we can move straight to the whole bit of the preliminary results, whereby we are using the line bit. And from here, we can see that the image shows the eyes, the mouth, and can be able to predict the different facial expression. And then from this, you can see the areas with green, the ones that are used for classification of the image. And that's what the line uses. Then from this, we can be able to tell that, okay, this is an angry person. And then from there, we can move to the conclusion of our work, whereby in our present day study demonstrates the feasibility and the potential benefits of incorporating the explainable AI into real-time micro-expression detection systems, and the foundation of successful communication and interpersonal relationships is the capacity to identify and understand their emotions. In the future, we plan to implement transfer learning techniques into our research and explore more explainable AI techniques, for example, the GradCam, able to enhance our model's performance. And these are some of the papers that we did review within our literature review that we cited out at the beginning in the table. Thank you very much for tuning in. Yeah.